Let's start from the beginning and do a little recap. Okay, this is our recap. Okay, so we are starting with chapter 4. We're doing a little recap on what we have learned so far about chapter 4. So chapter 4 is about work done and mechanical energy. So for work done, we have discovered that work done equation is actually W. W is the notation for work, and this is going to be equal to F dot delta X. When you expand this equation, a dot product, you get F cosine theta delta X. What is delta X? This is displacement. F is the regular force that you know. Now, the unique thing about work done is that it is a scalar quantity, which means that it is not going to have direction when you calculate for it. And the force that is acting on the object and the displacement, the force needs to be parallel to the displacement. For example, I have a force that is going in this way. I am only interested in the parallel component that is acting in the same axis as the displacement. So in this case, the force punya component that is acting in the same axis as displacement is F cosine theta. What about F sine theta? F sine theta is perpendicular to the displacement, so I don't want that. Work done punya equation is only the parallel component of force times with displacement. So this guy, we don't want it, it will become 0. So if you put it into the equation, F sine theta, the angle between F sine theta and delta X is going to be 90 degrees. Okay, this is work done, and this is delta X. So when you have a sine of 90, sine of 90, is it 0, right? Sekejap, saya pun confused. Sine of 90. It's 1, sorry. Salah angle. Kita nak cari angle yang ni. F cosine theta. It should be a 0. Sekejap, saya punya math tak betul. F sine 90 is not. Sekejap. Oh sorry, we are talking about the perpendicular. We are talking about the dot product. So dot product memang cosine je. Sine tak ada. Sine punya component ni tak ada contribution dalam work done. So it's going to be a 0. So any perpendicular force is not going to be in work done lah, because they only want the parallel component, and in this case it is F cosine theta. Now if you have an angle over here instead, okay, tadi abaikan tadi saya cakap F sine theta delta X equation 2 is not right. You just want the parallel component. So if I have my theta over here, don't use orange. If I have my theta over here, okay, abaikan yang ni, and I have a force, which means that if I want to resolve this guy, it becomes F cosine theta of something, and this becomes F sine theta. Now this is F sine theta, but it is still the parallel component with respect to the delta X. So this can be your equation. Okay, W equals to F sine theta. Asalkan dia parallel to the displacement boleh. Tadi saya salah sebab tadi angle kat sini, tapi saya nak ambil force yang kat sini. Force kat sini tak contribute to work done. Okay. So again, this is my F cosine theta. This is my new theta. Theta ni tak ada. So this will become F sine theta. And the parallel component that is the parallel component of force, the force that is parallel to the displacement is F sine theta. So this is going to be your equation. Now another example for down here is force going upwards. So if you resolve this, you would have F, let's say our angle is here. You would have F sine theta over here and F cosine theta. The axis that touches the angle gets the cosine. Now our axis, our displacement is to the right, but our force is to the left. They are opposite direction and they have an angle of 180 degrees. So 180 degrees, cosine of 180 degrees would give me -1. So this would give me a negative work done. So this would be F cosine theta delta X, and in this case you would have F. Negative work done. Okay, so work is negative when the angle is greater than 90, and work is positive when the angle is less than 90 with respect to the delta X. Excuse me. So that is your recap. Kita dah tengok ini juga rasanya. So remember, you always have to resolve the force, find the parallel component to displacement. Okay, and we already talked about this one. Work can be positive or negative, and work ni dia punya equation is force times displacement kan. So you would have different types of forces. You have the F push, you have the mg force, you would have the R force, and what else? Friction maybe if this is not a smooth incline. So you have different types of force, and these forces would each contribute to work done, either positive or negative. Nanti in the end, the work done on the object is the net work done. And how do you find that? It will become net F times the displacement of the object. So let's say the net force in the same direction ataupun in the same axis as your displacement is this way, right? Delta X. So the net force that is parallel to the displacement is Fp, and maybe a contribution from mg sine theta, because this is mg cosine. So mg sine theta is in the parallel axis, and Fp is also in the parallel axis. So in Fnet, your Fnet would be a summation of these two guys darab dengan delta X. So we are learning this in this topic, in this chapter. The net forces times with the displacement will give us the net work done on the object. Okay, so let's look at this one again. The man is pushing the piano up the plane. The box moves upward. The box moved by upward. Apa tu? By upward force. The work done. Sekejap, saya tak faham apa yang tulis ni. The box moved by downward. What is that? Downward force kot. Work done by gravity. The force of gravity is positive. Work done by pushing force is negative. Oh, movement dia. The box moves upward. Benda by-nya. So this is the motion. Up the incline. Not upward. Okay, so if our box is pushed up the incline, motion dia macam ni, maksudnya lelaki tu berjaya lah tolak kan, dia tak adalah tertolak oleh piano tu. So dia berjaya tolak, which means that this is the displacement of our object, and the work done by the force of gravity is negative. Sebab kita ada mg cosine theta here, and we have mg sine theta here. Mg sine theta and delta X are in the opposite direction, therefore work done is negative. The work done by pushing force is positive. This is the pushing force. It is in the same direction as delta X, therefore your work done is positive. And then sama juga, what if the piano jatuh ke belakang? Walaupun laki ni tolak tapi dia tak cukup kuat. So piano tu ke belakang, dia tergelincir lah. So the motion is this way. So this is your delta X. So again, we have our mg sine theta here, and we have our Fp over here. If the motion of the box is the opposite direction ataupun down the incline, the pushing force gives a negative work. The pushing force is in the opposite direction with the displacement, therefore it will give you negative work. Work done by the pushing force is negative. And mg sine theta is in the same direction as displacement, therefore the work done by the force of gravity is positive. Okay, so sama direction positive, lain direction negative. Tapi force has to be parallel to the displacement. Okay, so if there are a number of forces acting on an object like I mentioned to you before, we have reaction force, we have the friction force, we have a pulling force, and we also have mg. Now they are asking what is the total work done. So here you can see that mg dot d P dot D, D is this guy over here. The motion is to the right. This is D ataupun delta X. Lama tak nampak. D ataupun delta X. Okay. mg.d, p.d, n.d, f.d. So, diorang letak tambah macam ni, tapi kita tahu kita tak boleh tambah vectors easily like that. You can write it into an equation, but you can't add the values just like that if they have angles. They have to be in the same axis, baru boleh tambah. Kita dah belajar ni dalam chapter 3 and chapter 2 and chapter 1. Okay? Need to be in the same axis. So you can write it like this, no problem. But vectors cannot be added easily like that. So you have to know what is the net force acting in the parallel direction to the displacement. And in this case, the only the only forces that has a parallel component, the only forces that has the parallel component in the direction of displacement is this guy. Okay, so this is going to be P cosine theta, and this is going to be F. Mg tak ada contribution, N tak ada contribution because they are perpendicular. So the net force is only these two guys. So the net force acting on the object for us to find work done, ni specific untuk work done. So F is equal to P cosine theta minus F. So you put that in here and then times with the displacement. This is in the x direction only. Kalau kita cakap pasal Fy, then you would have N minus mg. But we're not concerned about that. So tak payah tambah kerja. So kita nak parallel component sahaja. Okay, next. Okay, so questions to ask when we are solving problems related to work done. What are the forces? We know this already from free body diagram. And in which direction is the net force? And specifically for work done, we want to know what is the parallel forces. Okay, sum of parallel components times displacement will give us total work done. Okay, so work done. So previously we talked about forces that are constant. For example, the guy pushing the piano exerts a force of 10 Newton. When you have that magnitude, that is going to be constant. Walaupun di atas ni is still 10 Newton, kat bawah ni still 10 Newton. You are assuming that the force exerted by the guy is going to be constant at all times. So these are called constant forces. Ataupun force yang tak berubah lah. But what if you have work done by a variable force? What does variable mean? Variable mean it keeps on changing over time. For example, macam mana, apa example yang sesuai? Okay, so awak ada, you have this toy that, apa, dia macam jukebox. Korang tahu ke jukebox tu apa? Dia pop out and then keluar clown. Don't know if this is a good example or not. Kejap. Okay, so let's say when you first put in the battery, kan, korang tahu ke jukebox tu apa? Kejap. I need to think of a more universal toy lah. Tahu okay. Kejap. Apa yang pakai bateri ya? Apa pakai bateri, lepas tu ada force? Dia ada penolakan. Macam dalam horror film, music box. Nah, saya nak benda yang ada penolakan. Objek yang boleh tolak tapi pakai bateri. Ada tak? Kereta mainan. Okay, boleh kita pakai kereta mainan? Okay, so siapa yang kasih tadi contoh tu? That's a good one. Cucuk lanun, ya Allah. Cucuk lanun tu apa? Cucuk lanun ni apa? Okay, Arman said. Okay, Arman said kereta mainan. Okay, that's a good example because if we put a car behind a box, Allah. Sorry lah, ni kereta Arman not my car. So Arman punya kereta, dia first letak, sorry ni toy kereta kereta mainan. So Arman letak bateri lah, bateri tu baru kan. Ya Allah, ni bateri apa ni? Okay, bateri tu baru. So bila kita tekan on kat kereta tu, it will give us a maximum punya speed lah kan. So dia akan jadi laju and dia akan tolak kotak ni banyak lah. So kita akan dapat delta X, and let's say the F applied by the toy car is going to be 2 Newton lah. Tak naklah banyak sangat, takut pula kan. So 2 Newton is exerted on the box by this toy car. But over time the battery drains, right? The battery drains. So your toy car tak laju sangat, and therefore the force now keeps on decreasing. So it becomes 1 Newton, then it becomes 0.5 Newton, then it becomes 0.25 sebab bateri habis. Bateri makin lama makin habis. So kereta tu pun makin lama makin slow, macam tu kan. So ditolak pun makin lama makin sikit. Dia punya force exerted on the box that it is pushing is getting weaker. So we call this type of force as a variable force. It changes over time. It's not going to be constant. And this actually applies untuk banyak benda in real world lah. When we say a constant value, sebenarnya kita assume ideal case. Mana ada orang yang tolak piano 10 Newton all the time. Dia pun penat kan. So sebenarnya tak constant, semua benda tak constant. So we are just assuming ideal cases yang mana forces adalah constant. But in reality, it's not like that. Okay, so back to this variable force. The force that changes in time. So for example, the elastic force, tadi saya cakap changes in time kan, ada situation where it changes with displacement as well. For example, elastic force of a spring. The example I gave you changed over time. This guy, it changes with respect to extension ataupun compression. So your spring, dia ada force exerted. Dia ada force yang dia exert kat kita bila kita tarik. So this is called, mana dia pergi? Okay. So this is your spring. Let me introduce you to spring punya force dulu. So spring punya force, dia akan always oppose the motion. So F spring, let's say saya tarik macam ni This is me, F applied. Bila kita tarik spring, kita akan rasa ada regangan daripada the other side. Bila kita tarik, spring tu macam jangan tarik. Dia macam, dia tarik kita balik lah kan. So it becomes harder to extend the spring with more displacement ataupun with more extension of the spring. It becomes harder sebab you have to exert more force. Kalau tarik sikit je force pakai, tapi kalau nak tarik jauh kat spring, rasa susah kan? Because there is a force called F spring, and it is a function of the displacement of the extension lah. I would say the extension of the spring. So lagi besar extension ni ataupun lagi banyak dia compress ataupun lagi banyak dia extend, lagi tinggi force yang diperlukan untuk kita tarik ataupun compress. And because kita ada force because we are actually trying to overcome the force exerted by the spring. Spring ni yang buat force So spring ni punya force is F equals to minus kx. And the force that we apply is going to be the opposite direction because we are trying to overcome that force. Therefore, F applied would be kx. Sebab apa? Vector kan? Vector terbalik akan jadi positif. So this guy is minus kx. Force that we apply is going to be kx. So lagi tinggi x, lagi tinggi force. Okay. So we also have another situation where this is also a variable force, electrostatic force between charges. So here you can see that the greater the distance, R ni is the distance between the charges. Let's say you have charge A and charge B. And the distance is between them is called R. The greater the distance between them, the smaller the electrostatic force. So lagi besar R, lagi kecil force sebab dia inversely proportional. When we talked about elastic force of a spring, this guy is proportional to X. Therefore, when X is increasing, therefore F is increasing. So F is proportional to delta X. In this case, F is proportional to 1 over R. The higher the R, the lower the F. The higher the X, the higher the F. So this is how you use the proportionality punya symbol tu. It's not a complete equation, but it gives you the relationship. This guy is called an equation because it is complete. When you use the proportionality punya symbol tu, it doesn't have to be complete. You only have to show the relationship. In this case, lagi tinggi X, lagi tinggi F. Okay, so in such cases where we have the force is not constant ataupun variable, we have to use integration. Okay, so don't worry, we're not using math here. Ada equation ni lah, dah ada siap dah. So, but the basis of these questions is actually integration lah, because this is the way to find out the work done when you have a changing force. This is the way. Memang kena pakai integration, but you won't have to integrate in this class. Compared to constant force, we only had to do multiplication, F cosine theta, delta X. It was easy when this is constant. When it is not constant, you have to integrate. However, you dah kasih shortcut dah. So the elastic force of a spring is F equals to minus Kx. If you want to find work done, we have to integrate this with respect to X, which is the displacement. When we want to find the work done, we have to integrate F with respect to displacement. So I can write this equation as X final, X initial, ataupun dua-dua adalah benda ni ialah delta X lah. X final minus X initial is delta X, and F is this guy minus Kx dx. So now you are integrating this equation with respect to X, because dia cakap kat sini kena integrate with respect to X. So buatlah with respect to X. Jangan pandai-pandai with respect to K pula. K tu constant. Okay, so dia dah buat dah kat sini. Kx 1/2 Kx squared. So dia substitute. Okay, kat mana hilang negatif ni, we are actually finding the work done by F applied. I told you F applied is actually this guy, minus Kx. F equals to minus Kx is by spring. Okay, F applied is the force that we apply untuk tarik spring tu. F applied is actually the force exerted by us. So this is equal to Kx. So we are actually integrating Kx sahaja, not minus Kx. So it becomes Kx squared over 2. And then you put in X2, X1 ataupun X final, X initial, boleh mana-mana. And then you have this equation. Sama juga untuk electrostatic force, but I don't want to tekankan this one because kita akan belajar next semester. Okay, so variable force in terms of graph, the area under the curve of force versus displacement graph, force versus height, force versus displacement, force versus radius ataupun distance between charges. So it has to be F in the y-axis and H in the x-axis, and the area under the curve will give you work done. The area under the curve will give you work done. In this case, dia akan cakap from HI equals to HF. This is from XI to XF. This one, R1 to R2. So dia nak tahu yang ni je. So you integrate the curve, you find the area under the curve. Now, what if the graph is below the x-axis? For example, let's go for this guy. Let's go. What if I have a graph like this? So dia ada force, mula-mula force tu constant, dia akan drop at a certain displacement. Contoh lah, saya tak tahu betul ke tak benda ni. Tapi ni contoh and mathematically it can happen. So this is X. So kalau dia patah balik, force dia tiba-tiba akan jadi negatif. So kat sini force is positive. Bila dia patah balik displacement dia, when the displacement is, this is not patah balik. When it reaches a certain X, the force becomes negative. Bukan patah balik dia punya X kat sini. So, macam mana kita nak kira area under the curve? The answer is, you have to make this guy find this area of this guy. Let's say this is area number 1 and this is going to be area number 2. So the total work done is area 1 minus A2. Whatever is above the x-axis is positive work done. Whatever is below is going to be negative work done. So the net work done is A1 minus A2 ataupun area 1 minus area 2. Okay, so this is how you solve it lah if they give you a curve. And you have like one part is positive, one part is negative ataupun below the x-axis. Kena tambah dengan tolak. Okay. Kalau duduk semua atas ke atas, then you just have to add lah. Let's say kalau nak situation yang kena tambah banyak kali. Macam ni lah kot. Okay, let's say this is F and this is X. So you want to know what is the area under the curve. Boleh ke curve macam ni wujud? Boleh. Mathematically boleh. Dalam real world saya tak sure. So this will become A1, this will become A2, and this will become A3. Now because all of the area are above the x-axis, you just have to add them together. So net work done is equal to A1 plus A2 plus A3. Tak ada yang minus sebab semua dekat atas. Okay, I have a question here. Oh, tak ada. Okay, so problem solving strategy. Read and understand the question, visualize and sketch the situation, identify all forces, ni wajib, sketch the free body diagram, identify the displacement, delta x. This is identify forces, identify delta x. Resolve the forces into its parallel direction and also the perpendicular direction to the displacement. And then calculate the work done by each force. Calculate the total work done, state your answer, do not forget unit. So work done agak senang sebenarnya sebab tak berapa complicated lah. In my opinion, ada lagi benda lagi susah lah. So this should be okay lah. Okay, it is going to be acceptable untuk korang score. Okay, boleh sebab ada lagi yang tajuk lagi susah. So please focus on this one and score this chapter lah. Okay, so a block of mass 25 kilogram is pushed 1.2 meter along a frictionless horizontal table. So this is a horizontal table and we are pushing a block of mass and it is 25 kg. Alright, so it's pushed 1.2 meter along a frictionless table. The delta x is equal to 1.2 meter. So this is the displacement. With a constant 36 Newton force. So the force applied on this guy is 36 Newton. Okay, ini bukan free body diagram lagi. Directed below the horizontal. So now I have to draw lah. Let's use a different color. Kenapa saya rasa macam silau? Saya rasa lampu ni kuat sangat. Okay. Buat betul free body diagram. Okay, free body diagram time. Wow, cantiknya kotak ni. Okay, so center of mass always we have a constant 36 force directed 35 degrees below the horizontal. Label your imaginary axis. In this case, our motion is this way. So kita boleh cakap this is our parallel axis. Okay, it is below. So below the horizontal axis by 35 degrees. Okay, please focus. This is the pushing force. It is directed below the x-axis by 35 degrees. And then what else do we have? The S is equal to 1.2 meter. This is the distance pushed ataupun delta X. I should label as delta X. Untuk projectile motion kan. Tapi sama je sebenarnya. 1.2 meter and then this guy is 25. So we are supposed to have mass lah. So this is my free body diagram. mg, m is 25. What else do we have?
Gila cairkan tu ada sekian. Kami buat lebih betul. Cairkan listrik gaisnya tu.
Okay, so everyone is saying R. R. Okay, what else? Is that it? It's a frictionless horizontal table, so we don't have friction. Safa is saying F. Yeah, tapi tak ada sebab dia cakap frictionless horizontal table. Okay, so these are the forces that we have. Now, it's asking determine the work done. So F delta X. F parallel delta X. Determine the work done by the applied force. So what do we have to do? We have to resolve this. So this becomes F. Lama tak berbeza dah pula warna dia. This becomes F cosine 35. And this is going to be F sine 35. Okay. Determine the work done. So we want to know only the parallel component, right? So the work done by the applied force is equal to F cosine 35 times with 1.2 meter. So this is our equation for A. Then B, the normal force. Minus ke doktor? Minus. Kenapa minus, Syafiqah? Kenapa minus ya? Sekejap saya baca. Below the x. Okay, but it is below the x. When you resolve it, is it in the same direction with delta x or not? What's the angle between f cosine 35 and delta x? 0, right? It's in the same direction. Sama direction, positive work. Can. We're not talking about f sine 35 here. Okay. So f cosine 35 is in the same direction as motion. Okay, dia tak bagi tahu motion ke mana. So I'm going to assume it's to the right. Okay. So motion kat sini to the right, f cosine 35 is also to the right walaupun di bawah axis. Tapi bila kita resolve, komponen yang parallel to displacement is going to the right as well. Therefore, it will become positive. So that is for A. Okay, B, the normal force exerted by the table. So it will become 0. Sebab it is perpendicular and tak boleh lah. F cosine 90. Oh yeah, it's supposed to be F cosine 90. And then the force of gravity. Force of gravity is also perpendicular to displacement. So C is also going to be 0. Tak payah kira, dah tahu dah. Perpendicular je kosong. And then D, the net force on the block. The net force on the block. So in this case, since we don't have any friction, I would say the net force on the block is, determine the work done by the net force on the block. Okay. So net force, work done by the net force. So this is going to be delta W equals to delta F times delta X. Ataupun, ya betul lah ni, dot So we want to know what is the parallel component tapi net force. So in this case, we only have F cosine 35. Let me rephrase that. So we want to know what is the total work done. So what I can do is I can add all the work done that I have found from each force. Okay, I know what is the work done by F cosine 35. This is the work done. I know what is the work done by R. It is 0. I know what is the work done by mg. It is 0. I know what is the work done by F sine 35. It's also 0 sebab dia perpendicular. So I can add all of these forces together in my network done. So it becomes F cosine 35 1.2 tambah kosong, tambah kosong, tambah kosong. F sine 35 sekali. 1, 2, 3, 4. 1, 2, 3, 4. So ada 4 forces Tapi yang ada value hanyalah F cosine 35 sebab dia sama direction dengan delta X and dia parallel. Okay, so let's see the answer. Okay, so F cosine, so this is going to be 36 cosine 35 times 1.2. Okay, the normal force is R cosine theta times S ataupun 1.2. So in this case, your R is perpendicular to the motion. It is going to be 90 degrees. Remember, dot product wants the angle between the force and between the two vectors, sorry. Dot product wants the angle between the two vectors. In this case, the angle is 90 degrees. So F dot S will give me R cosine 90 X. R cosine 90, silap equation kat bawah. R cosine 90, 1.2 R cosine 90 darab dengan delta X. Okay, so 90 degrees, apa-apa yang perpendicular akan dapat kosong. The force of gravity is this way and delta X is this way. What is the angle between them? 90 degrees. Again, mg cosine theta S, put in the angle, mg cosine 90 times 1.2 is equal to 0. Cosine 90 is always 0. Okay, next, the net force on the block. The net force on the block. So kat sini dia ikut cara yang sama saya buat tadi. Dia tambah semua work done. So akan dapat this guy sahaja. Sebab yang ni je yang parallel in the X, in the displacement direction. Any questions about that one before we move on? Kita akan take a 5-minute break before I go into the next topic. You can ask me any questions if you have any. Or else you may take your 5-minute break. Kita akan sambung 2:51 PM. F equals to 36. This is R. This is mg. Excuse me.
Doktor. Doktor.
Ni saya.
Saya nak tanya yang macam kalau kita nak kira total work by multiple force kan, kita nak kena tambah by axis ke macam mana tu?
Tambah by axis. Betul? Tambah semua x axis, tambah semua x komponen yang kita dah belajar chapter 3 dulu. Fx. Sebab fx akan parallel to delta x, right? So yang ni je yang kita nak tahu. Tambah semua, selalunya kita tambah fy apa, fx apa kan. Tapi kat sini kita nak tahu.
Betul.
Hello, sabar sekejap. Yes.
I got my phone.
Sekejap. Nah. Don't be noisy, okay? Okay, fine.
Thank you much.
Okay. Menjawab soalan ke Farhan? Okay ke?
Maksudnya macam kalau yang apa tadi yang F yang tadi tu F cos 35 kan? Itu yang kita kira. Yang untuk yang contoh kita nak dapatkan yang F tu, vektor F tu, kita kan dah resolve jadi F cos 35 dengan F sin 35. Jadi untuk cari apa, untuk cari jadi yang kita nak untuk cari net force untuk semua ni, untuk vektor F tu kita kena ambil F cos 35 je. Kan?
Betul. So dia ada dua cara. Satu cara is cari dulu delta fx darab dengan delta x. So yang tu tak payah fikir pasal dot product dah lah. So because you are already doing this, you don't have to use the dot product. But if you are using the dot product yang f dot delta x, then you would need, when you expand this, you have this guy over here. Yang ni adalah angle between the two vectors. Lepas tu saya lukis macam ni. Ni kalau nak pakai dot product, cari angle between the two vectors. In this case, F is 35 with delta X. R is 90 delta X. MG is 90 delta X. Tapi kalau nak pakai delta Fx terus, which gives us the same thing, kita akan dapat net in the Fx hanyalah F cosine 35 darab dengan displacement. It will give us the same thing. Okay? Sama je. Okay je dua-dua tu. Nak pakai approach mana-mana pun boleh.
Doktor.
Okay tak ada soalan dah. Alright. Okay, let's continue. I'm recording, right? Yes. Okay, so what we are talking about energy now. Just now we are talking about work done. Work done punya unit is actually joules, which is energy. So is work done a type of energy? Nanti kita akan tengok. So definition of energy is the capacity to do work. Lebih kurang lah. I wouldn't say work done is equal to energy, tapi it is related to energy and they have the same unit. But they are different things. Itulah yang peliknya. Okay, you need energy to do work. Okay, so this is how you relate energy and work done. So when you are doing work, you are losing energy. You become tired. When you are doing work, you lose energy. Therefore, you become tired. When you eat, you are consuming energy and you become energized, right? So benda ni dia interchangeable lah. So you need energy to make work. You need the energy to make work. I don't know. When work is done, there is a change of energy. So decrease in energy, you feel tired. Don't know who this is, but he is tired. Okay, and then positive work means that energy gain and the work is done on you. So you are gaining energy when you eat food. Therefore, work done, positive work done is done on you. And then when you are cutting a tree, I don't know when you would do this, but when you're cutting a tree, you are losing energy because you are using that energy to cut the tree, to do work on the tree. Work done
Wow, lemon.
on tree
Lemon.
is
Wow,
positive.
lemon.
Okay, work done on the tree is positive, but the work done on yourself is negative because you are losing energy. Energy tu pergi mana? Energy tu pergi ke untuk tebang pokok. So work done on the tree is positive, but work done is negative on you. I wouldn't pening-pening kepala sangat lah pasal term-term positif ke negatif ke. As long as you know how to use the equation. Okay, so the definition of energy is the capacity to do work. The energy is a scalar quantity. We know this already. The unit of energy is joules. Kejap. Alright, so energy can be in many different forms. And the ones that we are going to learn is kinetic energy, gravitational potential energy, and also elastic potential energy. This is related to spring. So elastic potential energy is spring. Any gravitational potential energy related to gravitational force. This is force by spring, force by gravity. Yang ni je, force by, don't know. Okay, so the energy of an object associated, kinetic energy is the energy of an object that is associated to its motion. For an object of mass m moving at the speed of v, its kinetic energy is defined as 1/2 mv squared. Kita dah tahu ni, this is like a famous equation. However, if our velocity changes, what happens to the kinetic energy? So if our velocity changes, we would have acceleration. And when we have acceleration, we would have force. And when we have force and we are moving, we would have work done. Force and moving object is equal to work done. Okay, so you can substitute F equals to MA S, and then you have the equation V squared U squared plus 2AS. This is from linear kinematic equation. You rearrange this to have A as your subject, and this would be V squared U squared minus 2S. Betul ke? Yes, V squared minus U squared divided by 2S. So this is going to be A. You substitute that in here. S is cancelled out with S. So you are left with 1/2 mv squared minus 1/2 mu squared. Just now, we talked about when the V was not changing. So this is the kinetic energy. But when it is changing, it becomes work done. When your kinetic energy changes, it becomes work done. In this case, it is 1/2 mv squared minus 1/2 mu squared. There is a change in your velocity. There is a change in your velocity. And work done is equal to the change of kinetic energy. It's not equal to KE. It's not equal to kinetic energy, but it is equal to the change in kinetic energy. Kena ada perubahan, baru ada jadi work done. Okay, so the work done on the object is equal to 1/2 mv squared minus 1/2 mu squared. This is known as the work energy theorem. This is K final because this is V final, right? V is final, we know this. K final, this is kinetic energy, the final kinetic energy of the object. And this is K initial, the initial kinetic energy of the object. So if you started with 10 meter per second, you are moving and then your speed increases to become 20, you would have 1/2 m10, then 1/2 m20, assuming that your mass does not change, your V changes, therefore your kinetic energy changes. This is equal to work done. Work done is the change in KE. I cannot stress this enough. Kena ada change in KE. KE final minus K initial. This is known as the work energy theorem. Okay. So can this definition come out? Yes, it can. Apa-apa yang law, theorem, apa lagi? Law, theorem, hukum apa? Hukum law lah kan? Betul lah. Law, theorem and definition, I guess. Benda macam tu boleh keluar as your 1 mark punya soalan, 1 mark punya soalan sebab dia tak ada kira-kira kan. So you have to, what is the work energy theorem? It is when work done is equal to the change in kinetic energy, and then you write the equation. If you write K final minus K initial, where K final is the final kinetic energy of the object and K initial is the initial kinetic energy of the object. Okay, so looking at this equation, it would tell us that speed will increase if the work on the object is positive. So let's look at this. So this is going to be W positive. This means that K final needs to be greater than K initial. Now we expand this. Expand macam tu pula. When we expand this, kenapa saya lukis kat sini ya? Ada banyak tempat lagi kot. Sekejap. Let me... Alright, so kita nak tulis kat sini. Kita nak buat W positif. So K final kena lagi besar daripada K initial kan? So let me expand that into its equation. This is going to be 1 over 2 mv final, v squared minus 1 over 2 mu squared. Since 1 over 2 and m are the same, I can factor that out. Okay, bear with me. So this is v squared minus u squared. So if I want this guy to be positive, v needs to be greater than u. Maksudnya our speed will increase daripada u. Let's say u is 5, the v has to be greater than u. Let's say it's going to be 10. Then the work done is going to be positive when v is greater than u. However, when our work done is negative, we know that there is a negative, tadi tu positive change in KE. We know that if we have a negative work done, we know that we will have a negative change in KE. So sama juga step macam tadi, v squared minus u squared. In this case, v needs to be less than u, baru dia akan jadi negative. And this would be a negative change in KE. Okay, the speed will decrease. Maksudnya v akan jadi lagi rendah daripada u. So if you started with 10, your v might be 5. So that is a negative change in kinetic energy. You are losing kinetic energy. When you become slower, your kinetic energy decreases. Okay, so that was kinetic energy and the work energy theorem. Now we're moving on to potential energy. Potential energy is the energy associated to its position. For example, untuk potential energy kita ada dua yang kita akan cover, which is gravitational potential energy and also elastic potential energy. Sorry, I'm distracted with my kid. Dia buat pelik-pelik. Okay. So kita ada dua satu by Fg and satu by F spring. Okay, kenapa ada kaitan dengan force pula? Ialah sebab this is going to be, when we have a change in energy, we will have work done, right? So this is how we are going to relate these things to work done. Okay, so gravitational force due to the attractive force between the object and the earth. Let's just abaikan ini. You know what gravitational force is. Near the earth's surface, the gravitational force on an object commonly known as weight is given by W equals to mg. Okay. M is mass, G is acceleration. Due to gravity, 9.81, constant jangan tukar G. Direction of force is vertically downward. Okay, this is like, siapa tak tahu ni, tolong rotan diri sendiri. This is like, dah 3 chapter dah kita cakap pasal mg going downwards. So this is gravitational force. Dia intro balik into gravitational force. Now we're talking about gravitational potential energy, which is associated with mg. So consider an object of mass m. This guy is mass m. It's an object with mass m. It is raised from ground level. We would say this as 0, and it is raised to a height of h. Okay, so dia naik sebanyak h. So I would say Sy, the displacement in the y-axis would be h minus 0. So it is h lah. Okay, ataupun we can say this as delta y. Sebab dia dalam y-axis. So the work done against the gravitational force. The word here is against. Against. So kalau kita nak cakap pasal work done by gravitational force, okay, bear with me. If we are talking about work done by gravitational force, I would say mg dot delta y ataupun delta h. Boleh, dua-dua boleh. Start h lah. Delta h This is the equation if I wanted to find out what is the work done by gravitational force, right? So mg dot delta h. The angle between them, mg is going down, h is going the opposite way. This is the displacement. It is the opposite way. What do we get for our work done if it is opposite? Anyone? Apa condition work done positif? Apa condition negatif?
Bila dia punya degree tu in between 0 and 90 dia positif. Bila dia antara 90 degree hingga 180 dia negatif.
Okay, betul. What is the angle between them in this case? Jawapan tu dah betul. Tapi apa angle dia kat sini?
Oh.
So kalau saya lukis kalau saya lukis these two vectors, lemak kecil sangat pula. If I draw these two vectors somewhere else, mg, and h is this way. What is the angle between them? What is this angle? 180 degrees, right? So tak nampak kat sini, tapi kena imagine lah yang mg ke bawah, h ke atas, apa-apa yang opposite sebenarnya is 180 degrees. Let's say I have a force to the right, I have another force to the left. They are opposite direction. What is the angle? 180 degrees. I have this guy over here, this guy over here. Opposite direction, same axis, 180 degrees. This guy, they are in the same axis, but opposite direction. The angle is 180 degrees. So if you wanted to expand this, this would become mg delta h cosine 180 degrees. This would give you a -1. Therefore, you would get a minus work done. If you were talking about mg, the work done by gravitational force. However, soalan ni dia cakap, bukan soalan lah. This tajuk ni kat sini, the work done against gravitational force. So kat sini dia nak cakap force yang opposing mg. So apa yang opposing mg? Kat sini tak ada lukis, tapi kita kena bayangkan sendiri that they are talking about a force that is going in the opposite direction. Itu saja. That is what it against mean. Against mean, saya tak tahu against maksud dia apa, tapi terbaliklah dia punya direction. So this would become, instead of cosine 180, this would become cosine 0. Sebab kita tengah cakap pasal mg yang going upwards. Dia bukan gravitational force, tapi it's a force yang terbalik dari mg. Kita bukan cakap pasal mg sebenarnya, kita just cakap value yang sama je. Macam mana saya nak bagi ni, tak pening kepala. So it's not gravitational force. Okay, tadi saya cerita pasal spring kan? I told you the spring had a force this way and the F applied is this way. They have the same value but they are in the opposite direction. Fs is equal to minus kx. Therefore, F applied is equal to kx. Does this mean that F applied is the spring force? No, it does not mean that. It just means that there is another force opposing the spring punya force. There is another force with the same value opposing the spring force. It does not mean that F applied is the spring force because spring force is just this guy. Sama juga case kat sini. We are talking about Newton's third law. Sama juga case kat sini. Mg ke bawah. I have another F applied. Let's just call this as F applied. F applied is going to be the opposite of minus mg ataupun it's going to be positive mg lah if we are talking about directions here. So it's going to be positive mg. Does it mean that it's the gravitational force? No, it's just a force that is used to bring up the ball by h. It is the force to bring up the ball, sebab ball ni naik atas kan, kita kena letak sesuatu force untuk bagi dia naik kan, dia tak naik tiba-tiba. Kita kena letak force kat dia supaya dia naik. So that is the F applied, and F applied is equal to the negative of the gravitational force. So the negative of the gravitational force is a positive mg. So this is how we get the mgh, dan bukannya negative w. Okay, kalau negative w dapat negative mgh. Tapi kita cakap pasal tangan yang tengah angkat bola tu. Kita tengah cakap pasal force that is exerted by me to bring the ball upwards. It should be equal to mg but in the opposite direction. Itu saja cara bola tu boleh naik ke atas. So therefore, work done is equal to mgh instead of minus mgh. Faham ke? I know that was confusing, but any questions? Orang macam tengah pening kepala. Any questions, guys? Okay ke? Okay, let me repeat myself a little bit. So kalau if I asked you, what is the work done by gravitational force? What is the work done by, what is, check, saya tak perasan. Sedang proses. Okay. Okay, so if I ask you, what is the work done by gravitational force? Then the answer would be minus mgh. Sebab apa? Sebab mg is going down, h is going up. Opposite direction gives me negative work done. But if I ask you, what is the work done to raise the ball against gravitational force? What is the work done? Kalau saya buang perkataan gravitational force ni lah, saya buang je. What is the work done to raise the ball by H? The only force yang dia kena overcome in this case is F equals to mg. So dia kena apply F equals to mg tapi opposite direction. Therefore, the work done to raise the ball by H is going to be equal to positive mgh. Sebab anggaplah ni tangan saya. Saya kena exert some force which is equal to mg. Baru saya punya bola tu boleh naik by h. Okay, so I hope that's okay. Alright. So we have a new equation. It's called UG, potential energy equals to mgh. So if your ball is up here, this is height 1, your potential energy of the ball is mgh1. If the ball is raised up further, your potential energy also increases mgh2. So if I ask you what is the change in delta U, it will become mgh2 minus h1. Why is delta U important? Because we want the change in energies to find work done. Sama macam tadi. We wanted to know what is the change in kinetic energy which was observed through the change in velocity to find out what is work done. Tadi kita belajar pasal W equals to change in KE. Now we're learning about the change in potential energy is equal to work done. So bila dia bergerak by a height, you would get work done. If it goes down by a height, you would get work done as long as there is a change in the height. Sebab G takkan berubah, mass takkan berubah. So yang apa yang berubah kat sini H sahaja. Okay. So your next equation is W equals to delta U equals to mg H2 minus H1. This is H final minus H initial. Okay, yang ni saya dah explain tadi. The work done by gravitational force. So mg is going down here, tapi buku ni dia naik atas, motion macam ni. This is motion and this is mg. Dia terbalik mg ke bawah, motion ke atas. This is work done by gravitational force, not against gravitational force. This is by gravitational force. Maksudnya gravitational force yang buat work done. Kita nak tahu apa work done by gravitational force. So, to tahu motion ke atas, mg ke bawah, therefore we can expect a negative work done. So therefore this would be negative delta U ataupun negative mg delta H. Okay, you can expand the equation lah. Okay, any questions about this one? Sebelum saya masuk elastik. So, berapa? Minus mgh, yeah. Any questions? Is everyone okay? Sekejap Okay, so now we go on to elastic force. So I told you earlier, I introduced you elastic force is actually from the spring. So the force due to elastic spring when compressed or stretched. This is called the elastic force. So your displacement kind of work done is force and displacement, right? So your displacement for the spring is either the spring getting stretched. This is the original state of the spring. This is the spring being stretched or extend. And if you were to compress, it will become like this, lagi rapat lah. So you have two states here. Either it's going to be extended or it's going to be compressed. So in this case, this is your original position. Your displacement would be from the original position to the length of the spring that was extended. So this is your delta x. And sama juga dekat sini, when you are compressing, you are measuring delta x di sini with respect to the original state of the spring. Okay, so delta x bila extended, I think is positive. Kejap, saya tak sure. Bila tarik, positif, betul lah. Bila tarik, bila ke kanan akan positif, bila ke kiri compress, dia akan negatif. Nanti kita cakap lagi lah pasal ni, more in detail. So experimental results show that elastic force is proportional to the amount of deformation, compressed or stretched. Tadi I just told you, you have your displacement of the spring either to the right or to the left, depending on whether you extend the spring or whether you are compressing. The force depends on position only, because why? It is minus kx. And again, I told you forces, I did not tell you yet. Forces selain daripada friction is called conservative force because it does not make the system lose energy. Apa-apa force yang tak bagi system lose energy is called a conservative force. Whereas a force that makes the system lose energy, such as air resistance, such as friction, is called a non-conservative force. So in this case, this guy, the elastic force, is called the conservative force. Okay, next. So Hooke's law gives the force as F equals to minus kx. So K is the spring constant. It is dependent on the material of the spring. So kadang-kadang spring tu lagi keras, kadang-kadang spring tu lagi lembut. So lembut atau keras determined by K, ataupun K determines the whether the spring is hard to extend or very easy to extend. So K tells you the behavior of the spring, whereas X is the displacement ataupun the extension or the compression of the spring. The value of K depends on the spring. Yeah, betul. So F is a restoring force. What does that mean? It means that when you apply some force to extend the spring, it wants to go back to its original position. Sebab dia nak restore balik original position dia. Dia nak restore. Restore means go back, right? So if I apply 10 Newton to the right, the spring said, I don't want this to happen to me. I don't like this change. So dia nak restore balik to its original. So dia akan apply minus 10 juga. So dia akan cuba lawan lah. Dia akan cuba lawan apa-apa yang saya bagi. Kalau saya bagi lagi tinggi dia akan tarik. So if I tarik by 20 Newton, the spring said, I want to restore this spring back to its normal position. So I will apply negative 20 Newton as well. Dia akan oppose anything that is applied to it. That is what restoring force means. It will always try to restore back to its original position. So elastic force is not constant, but it depends on the change on the length. So bila kita plot this graph, F equals to Kx, in this case, we are talking about F applied, which is F equals to Kx. So as you increase your X, your F also increases proportionally. As you increase your X, your F also increases proportionally. So F is proportional to delta X. F is proportional to delta X. What if F is constant over X? If it is constant, your graph will look like this. So yang ni adalah constant force. But we know that the elastic force is a variable force. Dia berubah mengikut X. So dia akan ada slope lah. When with increasing X, it will be increasing in force. Next one. Okay, so when we have force and displacement, kita tahu kita akan ada work done. So how do we calculate the work done for elastic force? So here they've used integration because it is a variable force. They use integration in this case. And they found out that, we're not going to do this. They found out that mana equation dia? The equation is 1 over 2 kx squared. This is your elastic force. This work is stored as elastic potential energy of the object. This is called elastic potential energy. It is called elastic potential energy. The work done against elastic force. Sama macam tadi, sama macam MGH tadi. MG ke bawah. Bola nak naik atas. So saya kena apply MGH yang sama value untuk naikkan sebanyak H. This is the work done against gravity, against Fg. This was the situation for gravitational potential energy. For elastic potential energy, ni kat y-axis. This one is happening in the x-axis. We are doing work against the elastic force. So saya kena apply force yang sama dengan this guy but in the opposite direction supaya kotak ni boleh bergerak ke kanan. So in this case, F applied and delta X. F applied is Kx. Sorry, you have to integrate. So you would get 1 over 2 Kx squared. Tak boleh darab macam tu je. So kena integrate. So it becomes 1 over 2 Kx squared. Sebab tu dia positif. Sebab kita tengok F applied. Sama juga kat sini. Kenapa dia positif? Sebab kita tengok mg applied. The force applied is equal to mg. Okay. So where K is the elastic constant of the spring. Again, this depends on your spring. And X is the displacement from the unstretched position ataupun original position. Okay, ni macam awal-awal belajar chapter 3 dululah. Banyak gila nak kena fikir apa benda ni, banyaknya doktor cerita. Memang macam tu awal-awal. Nanti lama-lama kita akan biasa. Awal-awal memang susah sikit. So original position So X is the displacement from the unstretched position or the original position. Now look at this one. This is the original. So I can label this like this sebab kita nak tengok movement of the box. So if I compress, saya tolak kotak ni ke kanan, ke kiri. Saya tolak ni ke kiri. So I am compressing the box. I'm compressing the box. Therefore, akan ada delta X of the box. The box moves together when I compress it. So, saya akan ada F push dengan delta X. So, this is going to give me work done is equal to 1/2 kx squared ataupun 1/2 k delta X squared. Kalau work done kena delta. And then if I'm stretching, F stretch, akan ada delta X sebanyak sini. Ambil daripada tengah-tengah kotak. Tadi saya mula kat tengah kotak kan. So akhirnya saya kena ambil daripada tengah kotak jugalah. So this is my delta X over here. From here to here. Daripada original, from here to here is my delta X. So that is how you determine your delta X. Okay. So work done, like I told you before, it has to come from the change in energy. So in this case, we are talking about change in elastic energy, elastic potential energy. So this equation becomes 1/2 K. K does not change, it is a constant. You have x2 squared minus x1 squared, or this is going to be x final and x initial. Boleh, mana-mana boleh. So in this case, your x2 is a positive value. Bukan positive value. It's a bigger value than x1. So you would get a positive. Tak apalah, nanti kita buat example. Susah pula nak cerita macam tu. Okay, so the work done by the elastic force to compress or extend a spring is, yes, I told you already this one. So it becomes from x1 to x2. Oh, sorry. This is, okay, let me rephrase that. So the work done to change the position of the object is the difference of the elastic potential energy of the spring. So in this case, we are talking about F applied. Sebab saya nak tahu berapa force yang saya kena apply untuk change the position of the object. Okay, so this is what this slide is talking about. But in the next slide, it's asking what is the work done by the elastic force to compress or extend a spring. Of the spring ni patutnya. Sebab dia negatif. Sekejap saya takut slide ni salah. Kejap This means that the spring that you need an equal amount of positive external work. This positive. Yes, it's talking about the spring. So let me write that. The work done by the elastic force of the spring. The work done by the elastic force of the spring to compress or extend a spring from x1 to x2 will be a negative work done. Tadi kita cakap positif. Tadi kita cakap pasal negative U, positif. Sebab ni was F applied. This guy is talking about F spring darab dengan displacement. So dia akan jadi terbalik. So kalau kita punya F applied positive work done, then elastic force punya work done, elastic force of the spring punya work done will be negative. Dia akan terbalik. Macam tadi juga. So F applied ke sini, kalau kat sini positive work done, therefore F spring would have negative work done. Kalau work done by F applied negative, therefore your Fx would have a positive work done. Dia akan terbalik sebab F dia terbalik. Sama juga macam tadi, if mg is going down and h is going up, you would have positive work done. You would have negative work done sebab dia terbalik. But when you are talking about F applied is the opposite direction to mg, but it is the opposite direction to mg, but in the same direction as h, you would get positive work done. Okay. So what if your h is going down? Mg is also going down. You would get positive work done. But the F applied is going to be at minus F. Dia akan terbalik lah. So that's the whole point. Okay. So now we are talking about total potential energy. 330 baru. Right now we are talking about the total potential energy. So consider an object of mass m attached at the end of a vertical spring. When this spring is stretched, the force acting on the object is gravitational force, mg, elastic force, kx squared. So this is going to be F spring. Dia akan cuba tarik kan, dia akan cuba restore. Mass ni cuba tarik ke bawah. Spring ni tak suka, dia tak suka berubah. Dia akan cuba naik ke atas. So the force by the spring is going to be going upwards. So the potential energy of the object must be due to these two forces. So kita tengok kat sini, dia akan bergaduh. Taklah bergaduh. Dia akan cuba lawan each other lah. Kalau mass object lagi kuat, if mg is greater than fs, then the mass will go down. If the spring force is greater than mg, then the weight will be going upwards. Boleh fikir logik lah. Kita letak objek, ada spring, kalau mass tu berat gila, dia akan jatuh sebab mg lagi besar dari fs. But if mg is smaller than fs, then it will go up. So daripada sini, the motion is determined by the net force. So you would get delta H either going up or going down depending on which force is bigger. Daripada situ, kita tahu kita akan dapat work done. Okay. Okay. So dia suruh tambah lah, dia suruh tambah these two potential energies together because they are the total potential energy. So the first one, the first component is mgh, second one is the elastic force. So mgh and 1/2 kx squared. So if I were to contoh lah, kejap. Do we have? Okay, so we have an example. So a spring is extended by 20 centimeter. Okay, everyone, wake up, wake up. A spring is extended by 20 centimeter when a force of 150 Newton is applied to it. Okay, so soalan B ni dia cakap spring is suspended vertically. So we can assume that this is horizontal. Okay, so this is a horizontal spring, which means that it is going to be on a table. So saya lukis dulu. So this is my spring and extended by, let's say this is the original position. And kenapa original position saya macam tu? So dia akan extend by 20 centimeter. Okay. So I take this as my point of reference and this as my point of reference. Saya ambil yang hujung sahaja. So this one would tell me my delta x is 20 centimeter ataupun 0.02 meter. When a force of 150 Newton is applied, we're talking about F applied here. So maksudnya ada orang tengah tarik spring ni by F applied. Ataupun what do you call tangan? Tangan tak ada lah benda-benda tu. Okay, so ada orang punya tangan lah, dia tarik, F applied. Saya nak cakap sebuah tangan tadi, merepek gila. So F applied, tarik spring, pakai tangan lah. So it extends by 20 cm and this force applied is 150 Newton. So, macam mana kita nak relate dengan equation elastic force? Force of applied, F applied is equal to Kx. Remember, we're talking about F applied, not F spring. So F applied is Kx, not minus Kx. So K tak tahu, F kita tahu, F is 150. And then we don't know what K is, it's not given, but we know the delta X. We know the delta X. So our delta X is 0.2 meter. This is Newton, this is meter. What is the unit of my K? Can anyone tell me? Saya tak suruh cari value saya tanya what is the unit of K? Come on anyone? Okay, diorang dah cuba jawab dekat chat. Newton millimeter. Millimeter. Oh, Newton meter. Newton per meter. Okay, Newton per meter. A lot of are saying Newton per meter. Okay, betul. Senang je kan, rearrange je. So K would be Newton. Kita bawa ni ke sini. You get Newton over meter. Yeah. So the value is going to be 150 divided by 0.02. Syntax error. 150 divided by 0.02. So I would get K as equal to 7,500 Newton per meter. Any Newton. Okay, and then this spring is then suspended vertically with a load of 8 kilogram. Ambil kau. 8 kilogram terus. So tadi horizontal spring on a table. What if we now attach this spring up the ceiling? Jangan ceiling, tinggi sangat. Up a table lah. Table punya bawah tu. I don't know what it's called. So this is our spring before the mass. And after the mass, attached to it, it would become compressed. Is that right? After I attach my mass, the spring becomes compressed. Betul ke salah? No, okay. No, okay. Ada orang masih fokus. Thank you. So when I attach the mass, my spring dangles down. Alright, so this is my mass. So dia akan jatuh ke bawah. So this spring is then suspended vertically with a load of 8 kg. Berat gila. Lagi berat dari beras 5 kg. So attached to its lower end. Calculate the energy stored in the spring. So now this is the same spring. This spring, maksudnya it is the same spring. The spring that we know that has K equals to 7,500 Newton per meter. Can we calculate what is our energy stored here? And how do we do that? What is the energy stored in this spring? Anyone has any idea? So basically, dia meregang, betul. So basically, it's asking what is the net, how do I say this? Kilogram to Newton. Doctor, the length should be 0.2. Is it? 20 centimeter convert to meter bahagi berapa? Kilogram to Newton. Saya pun tengah mengantuk ni. So, how do you convert 20 centimeter to meter? 0.02 kan? Ke saya salah?
Bagi 100.
Bagi 100.
Oh, so it becomes 0.2. Sorry. Divide by 100. Okay, thank you. 0.2. Bagus tak saya? Saya tengah ngantuk-ngantuk pun saya boleh bercakap dengan kuat lagi. Okay. So 0.2 is 20 centimeter. So you would get 750, I guess. 150 divided by 0.2. 750, yeah. So you would get 750 Newton per meter. Okay, so someone said in the chat, saya tak ingat siapa jap. Tiba sedih. Asal korang ni suka touching ah? Saya rasa kelas K7 ni suka touching. Tapi tak apa, baguslah. Okay, in touch with your emotional side. Tadi ada orang jawab kilogram to Newton. So Lukman is saying kita tukar kilogram to Newton. Okay, boleh. So kita tahu kita ada mg in this way. So 8 times 9.81. Okay, so 78.48 Newton. Down here, what else? What else should we do? We don't know what the displacement is. So macam mana kita nak cari displacement tu? Okay, so let me give you a hint. What does the 8 kilogram mean? Is it F applied or is it, what is it? Or is it related to MGH? Ada juga kaitan, tapi kat sini kita cakap pasal spring. So what does the 8 kilogram represent in this case? So if someone is saying, Afika is saying F applied, Yan is saying F applied, Lukman pun saying F applied. Okay. So in this case, kalau kita bayangkan dia horizontal, kita bayangkan dia horizontal macam kat sini. Ni tangan saya tarik. Saya kena tarik lah kan. By a force, so that is my F applied. Tapi bila saya terbalikkan spring ni jadi vertical macam case ni, tapi saya tak tarik pakai tangan, saya tarik pakai mass. Yes, it becomes my F applied. So my F applied is actually the mass of this guy. Saya tak payah pakai tangan. Saya bagi mass tu buat kerja untuk saya. Hidup saya senang. So my F applied here is 78.48. We know what the K is. Can we find what is the stretching of this spring? So Lukman is saying 78.48 equals to 750 over M. 750 over M. Does that mean? But yes, kita boleh pakai into our equation F equals to Kx. Kita tahu F applied apa. Betul. So F applied is 78.48. Our K is 750. This guy is in Newton. This guy is in Newton meter. What should our X be? Ta-da! So 78.48 divided by 750 dapat 0.1. 0.1. So X is 0.1. Unit yang tinggal hanyalah meter sahaja. Kalau saya bawa ni ke sini, N akan cancel out with N. I'm left with meter. So the unit for my X is should be meter. So betul ke 0.1 ni? Takut saya salah kira. 78.48 divided by 750. 0.1. So that is the stretching. PowerPoint ni dengki betul. So this is the stretching. Sekejap. I need to make this accurate. So saya ambil pada sini kan. So kena ambil pada hujung sini juga. So this is the stretching experienced by the spring when 8 kg of mass is applied. Ataupun F applied is 78.48. So you would get a stretching of 0.1. But in this case, it's a delta Y. Tapi tak apa, kalau korang label as delta X pun, fahamlah maksud dia apa. Kejap ada gangguan. Okay, so sorry ada distraction tadi. Anak saya cakap dia too tired for doing nothing. Okay, itulah cabaran yang ada. Alright, so we have the extension of the spring was calculated using F applied and equation elastic force lah. Okay, so we used F equals to Kx. F applied is the mass. Sebab mass tu tarik dia, so that it becomes the F applied. So we know what K is, so we can calculate what is the X. But kita tak habis cerita lagi. It's asking calculate the energy stored in the spring. So now we go back to our equation, which is the potential energy of the spring. Mana tadi? So, the elastic potential energy, apa ni? Kenapa definition dia macam pelik kat sini? Okay, so this work is stored as elastic potential energy of the object. So this is U equals to 1 over 2 kx squared. This is the elastic potential energy stored in the spring ataupun stored in the object that is extending or whatever lah, ataupun compressed. So kita akan pakai equation ni. Mana soalan tadi? Kita akan pakai equation ni. Mana pergi tadi? Oh Allah, jauhnya. Okay. So we can use this U equals to 1 over 2 kx squared. Is this going to be apa saya cakap tadi? Okay, never mind. Let's just use this equation. 1 over 2, 750, and then you have 0.1 squared. So whatever that is, 750 times 1 over 2 times 0.1 squared. So you get 3.75. The unit will be in joules. So let's see if this is the right answer. Yay! So again, they use F equal to Kx, dia dapat sama. So betul lah yang 0.2 tu memang saya tengah lalu. So when suspended vertically, your mg becomes your F applied ataupun Kx. You equate that together, you get your 0.1 extension. The amount of energy stored is equal to elastic potential energy. You use this equation when we are talking about the energy stored in the spring. Energy stored in the spring when it is extended or compressed. Pakai equation ni. Dia ada K. K tu refer to the spring constant. X to extension or compression. Okay, my question to you now is, kalau dia extend, kita pakai 1 over 2 kx squared and we get a positive answer. What happens if my spring is compressed? Would my U becomes positive or negative? Spring is compressed. What is the sign of U? Memang saya tak boleh cakap dah ni. What is going to be the sign of U? Positive ke negative?
Negatif.
Apa?
Negatif.
Negative. Let's see orang lain jawab apa. So, okay, so ramai jawab negatif. Okay, so let's look at this equation balik. So, kalau saya extend x squared, nak tukar jawapan tak? So, semua orang jawab negatif walaupun saya dah kasihin. Okay. So, x squared ni maksudnya hilanglah sign tu. Kalau displacement saya ke kanan, x squared positif. Displacement saya ke kiri, negative x. X squared kan? Positive x squared. So when I square something, the sign automatically goes away, right? So negative x displacement squared, x squared. Positive x squared, x squared. Tengok, saya cakap pun dah tak betul lah. So negative x squared is x squared. Positive x squared is x squared as well. Which means that it doesn't matter if it is going to the right or to the left. Extension dia ke kanan ke ataupun compression dia ke kiri ke apa ke. Tak kisah. Jawapan dia sebab x akan squared. Okay. So dia tak kisah sebenarnya. Yang kisah hanyalah force. Sebab force is F equals to Kx. So kalau positive X, positive F. Kalau F minus X, you will get minus F. Tengok kat sini lah. Dia proportional. Kat sini dia proportional to X squared. U is proportional to X squared. Tak kisah sign dia apa, dia tetap akan positif. Okay, so I think that's it. Saya pun tengah cakap macam tak betul ni. Positif juga. Pozotov, okay boleh. Pozotov pun boleh. Alright, so that is it guys. Kalau ada soalan boleh tanya. If not, we are ending our class here. Saya pun dah tak boleh nak mengajar. Lepas ni kita akan belajar energy transformation, equation baru. So kalau rasa yang what we have learned in the earlier topics tu susah, please do a revision. Sebab kita akan pakai balik untuk the next subtopic. Please do your revision Make sure you understand everything. Okay. Bye everyone. Have a great rest of the day.
Thank you,
Thank
Miss.
you, Doctor.
Bye-bye.
Thank you, Doctor.
Bye-bye.
Thank you,
Bye.
Miss.
Have a nice day, Doctor.
Terima kasih, Dok.
Terima
Welcome.
kasih, Doctor.
Welcome. Bye-bye.
Thank you, Doctor.
Welcome. Bye.